no stranger to Caltech. He was an undergrad here, and after he got his PhD at Berkeley on dark matter searches, he came back as a Sherman Fairchild Fellow and was a postdoc.
Millikan Fellow, actually.
Millikan Fellow. And he's now a professor at the University of Minnesota, and he'll talk to us about underground stuff.
Okay, thank you. It's very nice to be back. I guess, can I move this a little bit?
Yeah.
All right. I guess all of you know over the last few years there has been a growing interest in the possibility of building the third generation gravitational wave detectors underground. So this talk will be essentially a brief summary of some of the efforts that we've been doing along these lines. So I'll start off introducing what some of the scientific motivation behind this is, why we think it would be difficult to do this on the surface, and what in particular we could gain by going underground. And more specifically, in the second half of the talk, I'll probably focus more on the actual results that we've been getting from DUSEL. We were trying to essentially launch a new project under the name of Deep Underground Gravity Lab at DUSEL. And I will say a bit more about what the scope of it is, what our plans are, and some of these preliminary results that we're getting. Right, so everybody here, I guess, knows that the surface-based detectors will work at frequencies of 10 Hertz and above. The space-based LISA is designed to work at 10 millihertz or around there. And there is a gap in between. Of course, both of these are very well scientifically motivated. They have, each of them has a set of sources that they're targeting. And the question here really will be, can we probe the band in between 0.1 and 10 Hertz? Again, there is a number of sources that I will discuss in more detail in a minute. But essentially, the issue here is not just bridging the gap. There are there's a lot of additional science that we could achieve with an instrument that could work in this band. And this includes the stochastic background. I will say more about that in a minute, but we could essentially start probing some of the most interesting cosmological models with this kind of an instrument. There are also periodic sources, the in-spiral type sources, lots of different fundamental physics, high-energy cosmology, neutron physics, and so on. In the case of the stochastic background, we think of it in terms of the energy density rho, which can be expressed in terms of the metric. Is there a pointer, maybe? All right, finger it is. Okay, so we normalize that energy density with the critical density of the universe to get the spectrum omega GF, and that's related very simply to the strain power spectrum. There is essentially just this F cubed term, and that's really where this becomes relevant. Namely, if we take the advanced LIGO, say, or advanced Virgo type instrument and extend it to work 2 orders of magnitude in frequency lower than where it is now, so down to a Hertz or a fraction of a Hertz, then we could get essentially something like 6 orders of magnitude in sensitivity to omega. And since advanced LIGO will be sitting somewhere here at 10 to the minus 9 in omega, hopefully, 6 orders of magnitude could bring you down here, sufficient to start probing some of these most interesting cosmological sources, the inflationary models with various variations on that, with reheating, preheating, and so on, the cosmic strings, and others. Another interesting thing is that most of the astrophysical stochastic foregrounds that we're aware of today seem to be clustered either above or below this frequency band. So we may have a clear shot at this at the cosmological backgrounds. Now that's not entirely clear at this point because not many studies have been done on this. And one issue, for example, is we know that we'll expect a number of binaries in this frequency band as well. So taking those out probably will not be trivial. Nevertheless, it may be a possibility. The periodic sources turns out that actually most of the known pulsars lie in this frequency band between 0.1 and 10 Hertz, something like 90% of them. And as a figure of merit, within 1 kiloparsec, There's about 46 known pulsars in the 1 to 10 hertz band and only 8 in the 10 to 100 hertz band. The strange signals from these sources are expected to be smaller, but because there is a lot more of them, they might be closer, so we might be able to see some of them. The binaries, in this particular case, since this is a somewhat lower frequency band, compared to LIGO and Virgo, will be sensitive to higher mass binary objects. The merger frequency, the frequency of the last stable orbit of the inspiral is roughly this. So if we have about a binary of mass about 1,000 solar masses, we'll have the final frequency or the frequency of the merger around the 1 hertz or in the 1 hertz band. Similarly, the dominant mode of the ring down, given by this equation, for something like 1,000 or 10,000 solar mass binary ends up being below 10 hertz as well. So you can track these, or you can look for these more massive binaries. And one of the interesting astrophysical questions is, can you identify the origin of the intermediate mass black holes, which would be exactly in this mass range, 100 to 10,000. In particular, today there are two possible scenarios: the direct collapse, which would have no inspiral, and the accretion or merger, which would have inspiral. So observing this could allow us to distinguish between the two. And of course, there is a lot of fundamental physics. So through the stochastic background, one can start probing the physics of high energy scales, inflationary models, possibly cosmic strings or superstrings. The binary inspirals can also be thought of standard sirens, because they can essentially give us the luminosity distance from their signal. And if there is an electromagnetic counterpart to these, then we could also get redshift, and we could do the redshift versus distance type studies similar to what is done with the supernovas. And this would be essentially an independent probe of the dark energy for redshifts of order 1. Neutron stars, of course, we still don't know what makes them pulse. We don't know that much about their physics either. So different ways or mechanisms of producing gravitational waves from neutron stars could allow us to study their equation of state and so on. And then there is, of course, the graviton mass, speed of gravitational waves, or changes in the inspiral waveforms, and a number of other strong field GR type tests. All right, so can we do this on the surface? Well, this plot here is an expectation for what advanced LIGO in particular could do in the low noise configuration. And in particular, if we look at this, there are 4 important, if you want to call them fundamental noise sources that limit the performance of the detector below 10 hertz. Namely the radiation pressure noise, the seismic noise, the thermal noise, and the gravity gradient noise. And of these, I will focus on the seismic and gravity gradient the most. The radiation pressure and the thermal noise are being studied already, and there are different ways of addressing this through making larger mirror masses and non-classical states of light in the interferometer and so on. The seismic noise pushing from 10 hertz, which advanced LIGO will hopefully have, to 1 hertz or fractional hertz is a challenge, but in principle it should be doable. But the gravity gradient noise seems to be particularly difficult, essentially because you can't shield from it. So the gravity gradient noise is essentially a fluctuation of the local gravitational field that jitters the mirror. And one source is, for example, the seismic motion. So if you have the ground tilting one way, you will pull the mirror in that direction. A little bit later, when the wave passes, it will pull the mirror the opposite direction. And if you integrate across all directions on the sky, you get essentially noise. On the ground, there are other sources, the atmospheric fluctuations, and also the human factor and local disturbances that come into play. And I'll say a bit more about these. So the first estimate of, as far as I know, the first estimate of the gravity gradient noise on the surface was done by Peter Solson some 25 years ago. And I believe this curve here comes from that calculation. at 1 hertz, this calculation predicts strain equivalent noise at a level of 10 to the minus 20 per root hertz. And he also predicted that the atmospheric fluctuations will contribute at about the same level. There were several more detailed calculations following this, one done by Scott Hughes and Kip Thorne, and then another one by the Virgo collaborators. And they were much more detailed. They took into account various seismic modes and so on. But in the end, they got results that were very similar to Solson's. So in the end, if we were to take anything out of this, it is the fact that we have to go from 10 to the minus 20 to about 10 to the minus 23. So a factor of 1,000 suppression at 1 hertz of the gravity gradient noise. So can we do it on the, can we do that on the surface? So the way you could do this is, or you could try to do this, is by building an array of environment monitoring instruments, which would monitor the motion of the ground and the atmospherics, and then feed those signals to the mirrors and essentially cancel this effect. Now there are several problems with this. And I would think that they're very significant and difficult to achieve. In particular, when it comes to seismic, for example, the speed of sound on the surface is of the order of 500 meters per second, and typically it's less than that, 200 to 300. And at 1 hertz, this implies the wavelength that's of the order of a few hundred meters, much less than the arm length. Moreover, the surface soil is not really hard rock. It's very dissipative. There are diffraction effects going on. The modal structure of the seismic noise is very complicated. As a result, the correlation length of the seismic waves on the surface is small compared to the size of the detector. So you would need a very large seismometer array. The atmospherics are probably even harder to deal with. I'm suspecting that one would have to essentially equip the entire interferometer and really don't have a good idea how one could go about doing this. The local disturbances are includes the human factor and so on, but essentially people moving, traffic and so on couples in very complicated ways, not just through gravitational effects, but also through mechanical tilting and so on. So tracking all of this, and of course tilts or local disturbances will destroy the coherence or the correlation as well, which means increasing the number of instruments.
Vuk, can I play devil's advocate?
Yeah.
Those are all very hard, clearly, and drive you to, I can't say large numbers of complicated sensors and
yeah.
all that. But if an underground facility costs $1 billion, I can imagine going a long way towards solving the surface problem with $1 billion.
Well, it's not just the money. It's
fundamental. Are there really unsolvable things on the surface?
Well, when I think about it, there are at least 2 aspects of it. One of them, well, 3 if you think about the money and the number of instruments. But one is how do you understand, or what kind of information do you extract from all of these instruments? How do you choose what's relevant? Well, maybe.
The automated filtering techniques don't require you to know anything about the modal structure of the models.
Well, I would argue that the trouble is that you have variation on the surface. Yeah. So it's not... Yeah, but I don't know if you can really adapt that much.
Now, the point,
that's
one of the points is if you want to subtract a factor of 1,000 or more, you need to know your ground
exactly.
decision of 1 part in 10 to 3.
Exactly.
So if you get some subtraction from the fact that you go underground, then you need to know what's happening down there with only the decision of 30, and then starts increasing.
There's no doubt it's easier on the ground.
Yeah?
No, the question is very valid. Can you do it without, I mean, in principle, can you do it? Yes. If you had an unlimited CPU power and unlimited number of instruments, yes. In practice, can you do it? I feel it's very difficult. Maybe there are clever techniques that people come up with that will solve that problem, but it just appears very hard. Yes?
How far away from talking about a surface system?
So we don't know. I think that's really the correlation length. I suspect is of the order of tens of meters on the surface. It depends on where you are very much. And I imagine you would have to make something like 100 meter or more square, so that around each mirror. That's just for the seismic. Now underground, probably you don't need to worry too much about underground. You probably don't need to go deep.
I'm just saying, meter, 10 meters.
I think you can get all the information you need by measuring the surface. I suspect that's the case.
Again, for $1 billion, is it possible we can modify the surface? You pour a lot of concrete.
Kill all the people who don't like
We already did that.
Yes. So the seismic case is actually probably the easiest here. So what I'll present here is essentially what you could possibly gain underground. Whether it's possible to do it on the surface or not, at this point it's not absolutely answered. It may be, but one has to study it very, very detailed. So what are the advantages of going underground? Well, first, the atmospheric fluctuations are not there. The environment is much more controlled and much more stable. Things like ventilation are well understood. There are no, the human effect in particular is very, very controlled and limited. So you don't have local disturbances in various places that destroy the correlations and coherence. The seismic noise is reduced. It's reduced exponentially. There's here a calculation by Giancarlo Cella. The exponent, though, depends on the frequency. It goes as 1 over lambda. So at 1 hertz, you don't gain that much. At 1 hertz, maybe you get about an order of magnitude. Maybe more, maybe less. Depends how deep you go and what rock you're sitting in. There are also some measurements that were done in the past. These are done with borehole studies. I guess the curves that you are probably most interested in are these two. They show the suppression in the seismic signal at these two locations, one in Texas, one in Oklahoma, and the order of magnitude at 1 hertz seems to be achievable. So this is, in terms of sources, all of those 3 sources that I mentioned that dominate on the surface, you win by going underground. In some cases, a lot more than in others. But I think there are a few arguments that are, in addition to this, that would make our life underground in building this a lot easier. Yes?
Can you go back to the last slide? I almost understand. So, is the amplitude of the movement?
Yeah, I believe this is on distance to distance, or displacement to displacement ratios. Delta phi, what do you mean? You will get gradients, yes. So I'll talk more about that in a minute. We don't exactly know what that means in terms of gravity gradient, but I will say a bit about that. So as I said, there are a couple of arguments that are, in addition to this, very important, in addition to suppression of the sources. First is that the correlation lengths are significantly longer, and in particular, the speed of sound at the ground is something like 5 kilometers, so maybe 10 times, maybe more larger than on the surface. And also, the medium is much more uniform. There could be cracks and deformations and so on that will cause diffractive effects, but in general, the rock is much more uniform. And there are 2 consequences of this. One is that the gravity gradients are going to be correlated between the sites, between mirrors, say at the end stations or end station and corner station. And in particular, if you go to the extreme of 0.1 hertz, the wavelength becomes something like 50 kilometers. So the entire interferometer just moves in phase. Essentially, you have a suppression in gravity gradient noise. At the interferometer. In addition to this, because the correlation lengths are so large, you can get away with an array of seismometers that's much smaller. Now, how much smaller, we don't really know, but it appears to be much more plausible. And just mind you, because you have a factor of 10 suppression in the seismic noise, you only need to get another factor of 100. Now, a part of that 100 could go into one of these, and part of that could go into another, into the other. Exactly how it would pan out, we don't know. Another issue, which you just raised, is what is the gravity gradient noise corresponding to these seismic waves? And it's definitely going to be different from the surface. On the surface, the dominant effect is the heavy dirt replacing the light air, so surface waves. Underground, we will have to deal with bulk waves, and most likely we'll have to go several wavelengths away and integrate that. In particular, we started developing a finite element model, and essentially the first calculation we did was to see what the correlation length would look like for seismic waves alone as a function of distance. In this particular case, we assumed the speed of sound to be about 4 kilometers per second. We took longitudinal waves and looked at the coherence between 2 points as a function of distance. And it looks like that if we include something like 1 or 2 wavelengths, that should be good enough. It seems that the correlation length goes away on that kind of scales. And intuitively, you can understand that because the product of delta x and delta k for Fourier partners should be of order 1, which means the delta x will be of order lambda. So, and of course, if we have an imperfect medium, that all goes away, and the coherence length is even smaller. All right, so all of these are good, but what do we really know about underground? And it turns out that we really don't know much. We don't really know how deep we need to go, how the seismic noise changes as a function of depth, and how its correlation length changes as a function of depth. We don't know how much the rock and the rock content and uniformity or presence of cracks and so on, how much that sort of thing matters. Do we gain by building large cavities? And what does all this mean for the gravity gradient noise and how it constrains the design of an underground interferometer? These are all questions that at this point we really don't know the answer to. And the only way we can answer it is by going underground and actually making some careful measurements. So we really need to set up an array of seismometers across the depth and whatever available x, y horizontal dimensions we have, and just try to look how the seismic noise changes and how the correlation length changes, and try to combine it with a model of seismic noise to gravity gradient noise coupling to answer this kind of questions. All right, so this brings me to DUSEL. So many of you are probably familiar with this motion. DUSEL is a deep underground science and engineering lab. And in the words of John Kocher from NSF, it's an underground laboratory space providing infrastructure for science and engineering research. So the primary motivation for this is actually particle physics or astroparticle physics. There's a number of experiments that benefit from the low radioactive background because of the rock essentially shields from cosmic rays. And there's a process that's being pushed by the NSF to get this designed and funded. There was a solicitation 3 a couple of years ago that was awarded to UC Berkeley to develop the design for this MREFC candidate. Just last January, there was a solicitation 4, S4, where various projects were submitting proposals to make plans for the initial suite of experiments. So this is not actual proposals for the experiments, but just to get some money to do the design studies. And they're anticipating something like 15 million spread over 3 years or so. And sometime later this year, there will be S5, which will be the design, which will ask for proposals for the design of these first experiments. So this combination of S3, S4, and S5 is supposed to actually make the comprehensive project plan for DUSEL, including both the facility and experiments. The assembly of that whole proposal should happen sometime in 2010, and hopefully the construction will begin 2013 or so. In terms of funding, the NSF is projecting something like $500 million for this. Half of that will go to experiments and half to build a facility. I think there is more and more talk about others joining in, like DOE. So Homestake Mine in South Dakota was chosen to host this facility, DUSEL. This is an old gold mine. It's actually sitting on one of the largest gold ores in the gold ore bodies in the world, which is kind of exciting. It's very deep. It's actually the deepest mine in the North American continent. It's 8,000 feet. And it has hundreds of kilometers of tunnels and drifts and crosscuts and so on. It's very, very complicated. Now, because of political and other reasons, the lower half of that actually got flooded over the last few years. And there's a huge effort going on now to pump that water out. The level is currently at about 4,700 feet, and it is dropping. But there's also a lot of interest in what is available right now. There are a few groups that are trying to develop some experiments. We are one of them, but there are also geology groups and so on. In particular, there is something called DUSEL, the Sanford Underground Science and Engineering Lab, which has some privately donated money to provide infrastructure to these early experiments. And by infrastructure, I mean things like power network, maybe some lab space and so on. Safety, yes, that's a big thing, right? What's maybe even more important, the community there is really enthusiastic about this. There is a huge support from the local community to get this going. And our example, when Ricardo and I went there for the first time last February, we went there to do some quick and dirty measurements with car batteries and so on. And we went to something like a Pep Boys. And when we started talking to people there and they realized we wanted to do experiments with Homestake, they gave us a discount. So it is...
5% discount for the night.
Yeah.
They do a decent job in your car.
You have to run seismometers and laptops, but...
You said it's flooded for political reasons?
Well, it was...
because political reason impeded
yeah.
the project to start immediately.
It was privately owned, and the private company wanted to give it to the government, and the government kept stalling, and this company was just losing money, so they decided we're going to just stop pumping the water out. We're getting out of there, and by the time the people came back in, half of it was flooded. I should also mention there is actually a pretty large experiment that's supposed to go in there sometime soon, which is LUX. It's a liquid xenon dark matter experiment, and they're planning to actually go into Davis Cavern, where Ray Davis did his first neutrino experiments several decades ago, which is actually currently flooded. So they're waiting for it to become available. As soon as that happens, they will go in. And we're hoping that once that happens, the whole site will become much more lab-like. There will be more scientists around and more infrastructure to support them. So as I mentioned, most of the drive for DUSEL comes from this low cosmic ray background. But it turns out, and this was the way Stan actually originally proposed it, we can look at DUSEL also as a low gravitational background facility, gravitational and vibrational. And this, of course, is interesting to us. It turns out it's interesting also for other areas of physics, such as the equivalence principle tests. There are also some very interesting natural connections with geology, geophysics, and so on. I'll say a few more words about that. Last April, we had a brainstorming session in Lead, right near Homestake. And we had a number of conversations with geologists and engineers and NSF people. And from all of that, we emerged with an outline of activities that we would like to pursue over the next 3 or 4 years, the purpose of which will be to characterize the Homestake mine and to inform the design of an underground gravitational wave detector. But also there are some broader physics aspects of it, and I'll say more about it. So we have something like a collaboration emerging from this. In fact, Ricardo and Stan are members of this. There are essentially three directions that we want to pursue. One of them is this design of the seismometer array. I mentioned this before. We'll go after the frequency band between 10 millihertz and 10 or 30 hertz. Essentially study how the seismic noise changes as a function of depth and frequency, how the correlations change, and so on. And I'll say more about that later. The other direction, one other direction is to develop optical strain meters. So essentially mount mirrors on the walls of the cavity and then measure how they move with respect to each other. This would essentially be complementary to seismometers because they would be measuring differential versus the common mode that we get from seismometers. They would also be relatively insensitive to tilts, which are, as you all know, a big problem for seismometers. And then we could try interferometer configurations to probe the XYZ anisotropies and start distinguishing between different modes and so on. Yet another direction is to actually put gravity gradiometers down there. And these instruments essentially are designed to, they're based on torsion balances, and they're very sensitive to gradients of the gravitational field, but typically at frequencies that are lower than what we're interested in. Typically they work at 1 millihertz or so. An example of such an instrument is shown here. It comes from the University of Washington. And the projected sensitivity at 10 millihertz is of the order of 10 to the minus 3 atwash, which is 10 to the minus 13 meters per hertz. This is not quite good enough for us. It may be possible to do better by doing some cross-correlation techniques between two gradiometers or doing some, improving some hardware and so on. But in general, we might not be able to get a direct measurement of the gravity gradients at frequencies that we care for. Now, it may be possible to do some extrapolations, maybe get a measurement at 1 millihertz, and combine and do our measurements at 10 millihertz or 100 millihertz and above, and then try to extrapolate, use some sort of a model and so on. Now, an interesting twist to this is that these torsion balances are good for the equivalence principle tests. The principle, of course, says that every kind of material flows freely in the gravitational field in the same way, and GR is based on this. But most models that try to connect GR with particle physics violate this principle in some way. So, there are some speculations that a violation of this principle may have something to do with dark energy and dark matter. So the idea would be to have torsion balance and put different kinds of material on it and look at the acceleration towards the sun or towards the center of the Milky Way. And the advantages are similar to what we have in gravitational waves, namely the low seismic disturbances, stable environment, both in terms of gravitational gradients and the thermal fluctuations and so on. And then there are a few other cross-couplings that are worth mentioning. There is actually a number of projects that have already been proposed for DUSEL. Some of them are looking at this relation between fluid flow, temperature, and stress. So the temperature of the mine changes as you go underground. Now there is also water in it, and the water will be taken out. There will be some stress realignments and microseisms during the dewaterings and so on. So these geology projects are doing similar things. They have arrays of instruments that are trying to track this. There's also transparent Earth, which is trying essentially to have to make 3D images of seismic waves and what things essentially measure or deduce from the seismic waves the density non-uniformities underground and so on. And they'll typically work at frequencies at 1 hertz and above. So our array would be complementary, and there is a number of interesting points on which we could collaborate. There are also the torsion balances can be used for rotational seismology. It turns out that they would be very useful for measuring various normal modes, the rotational normal modes of the Earth, and so on. Another aspect of it is that this facility or the laboratory that we would set up there could be used to test new instrumentation. And we're already starting that with some of the accelerometers, but you could envision adding tilt meters and all sorts of other things in the future. All right, so I'll spend the rest of the talk essentially discussing where we stand, what we have done most recently over the last year at Homestake. So our first contact was in February 2008 when we essentially really just went to meet the people and so on. In the summer, we had this large push to start building the seismic array. And we have completed 3 stations so far at 3 depths, the 300, 800, and 2,000 foot levels. And each of these stations operates at least one seismometer and a collection of environmental monitors, the magnetometers, thermometers, and so on. Most of the work was actually done by Jan Harms, who was a postdoc in Minnesota, and Angelo Sajiva, who was a summer student at Caltech last summer. And we had a huge support from DUSEL. Tom Transinger in particular, who's a local geologist, spent all his time essentially with us and took us around the mine and so on. Of course, Ricardo and I went rotating there, and we had some also help from Nelson Christensen at Carleton and Winston Swan in Florida. That's right, yes. At the moment, we have 3 instruments that we're running there. One is STS-2 that we loaned from the LIGO lab. One is the GURUB that was provided by Carleton, and one is Trillium T240 provided by Minnesota. But for a couple of months, we had also 2 Trilliums that were on loan from Nanometrics, and they actually came. They were interested in the low noise site, so they brought their instruments and their data acquisition and left it with us for a little while. And we're also, since last December, running some developmental seismometers that were built by Verona's group in Salerno. And over the last few months, our data flow has actually stabilized enough that we can actually, we've gotten some interesting data, and we've focused a little bit more on the data analysis and some model development. So Homestake Mine, that whole area really has 3 formations. They're called Foreman, which is the oldest, Homestake, which is medium age, and Ellison, which is the youngest. And Homestake is really the relevant one for the gold. It's actually an iron formation, but it has a gold ore in it. And because of the various, because of geological history and the various deformations, the thickness of these layers vary. And the Homestake one in particular can be anywhere between 0 and something like 100 meters. In the end, when you look at some cross sections of this area, you don't see a clear cut between these 3 formations. Rather, you see this complicated ledge structure. So this black stuff is really the Homestake formation, and the Homestake mine was built essentially in an attempt to track this structure. So the structure is it's not trivial. It's actually quite complicated, but it's also well understood because the mining company actually spent a lot of time doing the research and making boreholes in various places, studying how the rock content changes. So this is a cross-section. I guess this is northwest to southeast, and the 3 stations we have are shown with stars. This is a 300, 800, and 2,000 foot level. This is the Ross head frame. That's the main shaft through which we can enter at this point. Yeah.
You asked about why it got filled. Here was gold, and they made a big open cut to take the gold away. And this is a funnel which is about a kilometer across by half a kilometer. So when it rains, the water goes in and down in the mine. So when they abandon and stop pumping, it rapidly filled up. But the mine in itself is not dry. If it wasn't for the water, rain water from there.
Compared to many other mines, it's actually very dry. It's actually probably about the biggest hole I've ever seen in my life. It's really impressive. You may have seen others. Okay, so this is probably more interesting. This is the XY, or the horizontal projection, if you like. So here it is, the Ross shaft, and these are the 3 stations, the 300 foot, which is close to the shaft. In fact, it's about only 250 feet from it, and it's the first station we built. And it's sitting in the Ellison Formation, in the youngest one. Then the 800 foot station is some 600 feet from the shaft, and it's actually sitting in one of the homestake ledges. And the 2,000 feet is actually our best station. It's about 2,600 feet from the shaft. And it's also sitting in the homestake ledge, but it's very far from the shaft and from any other work that goes on in the mine. And each of these stations, the way we built it, we have concrete slabs on the bedrock, so we have very good connection to the rock itself. And then we were advised to actually use granite plates which are leveled and put seismometers on them. This actually makes all the tilting issues, and it resolves a lot of the problems that you have traditionally with seismometers. And then this structure is put inside huts that are built from rigid foam, and I'll show you some pictures. We typically use more than one to suppress the ambient noise, and we have data acquisition sitting nearby, usually some 10 meters away in a separate hut. So this picture up here is our 300 foot station. You see there are 2 huts that we made from this foam. Inside of this one is where the instruments sit. So the seismometer, this board is where the environment monitors are. The thing on the top is a power supply, which is not there anymore, of course for noise reasons. This is a slightly different arrangement. This is on the 2,000 foot level, and there we actually got the chance to block off a part of the tunnel. So the way we built it was different. We used the walls and just put 1 or 2 extras around it to separate the volume. And this thing here is a hut where we have our PC that does the data acquisition. And typically the 2 huts, the instrument and the data acquisition huts, are some 10 meters apart from each other or so. I should say this is Angelo Yan and Tom Transiger. Now, in terms of the instrumentation, we have a printed circuit board that has thermometers and magnetometers sitting on them. They are then connected to a simple Dell PC that's running it has a National Instrument PCI slot, PCI card in it. And the same card is used to read out the seismometers, and typically we run 1 seismometer, but in some cases we have more when we want to do comparisons and huddle tests and so on. The data acquisition then is synchronized, so we do it locally. The data is required at each site, at each station, and then we have fiber links that link these stations to the surface computer. And every 20 minutes we have a scheduler that writes them down into, copies the data from these local machines to the surface one, and writes the data in the frames. And we haven't done it yet, but the idea is to actually add these frames to the Caltech cluster and make them available to a wider public. The PCs are all synchronized to about 0.2 milliseconds, which seems to be enough for the kind of studies we're doing. And of course, we have remote access to the Surface PC. So we can actually control all the machines remotely.
I presume there are times when there's human activity, and then during those times the seismometer's information is not useful. And how do you know? Do you have a monitor of that as well?
So there aren't that many times. I'll show you how the data looks like so you can get a feeling. There are some things that we just see that we won't be able to do much about. Every 12 hours you see people go for lunch breaks. But in general, especially in the 2,000 foot level, we're so far from everything that others are doing that it's remarkably stable. I'll show you some data in a minute.
It's not far in surface distance, but the same thickness of rock is quite effective.
So I guess I'll start with the data preliminary results here. So this comes from, as I mentioned, we had about 2 months period where the nanometrics people came to work with us, and really their motivation there was they wanted to compare their instruments with the STS-2 we had. So we had two of these trilliums and one SDS2 all running at the 2,000 foot level next to each other. And the data acquisition was actually done with the nanometrics system. So they brought their own thing. They knew what they were doing, so the data actually came out good. And Jan has then used a regression type technique to essentially identify the common signal in the three instruments and to subtract it away and to produce these self-noise curves. So you can here essentially look and compare the performance of the three instruments. It looks like that they differ at the very low frequencies, and we suspect that this is due to the magnetic noise, or rather the susceptibility to the local magnetic field. And we also have spoken with Nanometrics about this, and sometime this year, I think they should come out with a new version of the Trillium that will have different coils. I think copper beryllium, was it? I forget.
It's not the coils, it's the springs.
The springs that will essentially be insensitive to the local magnetic fields, and we'll see.
Nispan C, which is magnetic with copper beryllium.
So we'll see what that ends up implying for us. We also got a fairly good measurement of the noise at the 2,000 foot level.
So
And
what's the origin of the time-varying magnetic fields?
Solar wave.
yeah, or yeah, or local things. I mean, there are variations. I'll show you in a minute. That's probably 2 slides down. So, this is the seismic noise that as measured during that time at 2,000 foot depth, and I've sketched out what something like what a typical Livingston seismic noise level looks like. So again, at 1 hertz, maybe an order of magnitude looks reasonable. Of course, this probably depends on.
It's not equal to the Hanford surface noise.
Okay, it may be. I don't know.
I mean, it's better about 5 hertz.
Which one is better?
The 2,000 foot level is better than Hanford above 3, 4 hertz.
Okay.
About the same.
All right, it could be. So the environment stability seems to be actually quite a stable location. All of this data comes from the 2,000 foot level, and it seems that at least over this period of 12 or 13 days that we looked at in more detail, we had all of these varying to a fraction of a percent, the temperature, pressure, the humidity, and so on. The magnetic field, which you were asking about, also seems pretty flat. Nothing particularly in frequency range that we care for. At lower frequencies, though, if you look at trends over a few days, you see glitches, and we suspect that this has something to do with the shaft running and possibly pumps and so on that are used to get the water out. But we haven't tracked this down. So it looks like daily variation. Right. So this is one of the things that we'll try to pursue. These are the measurements that we've done with our instruments. These are not quite as nice as what you saw before with the nanometrics instruments. And essentially the issues are that the noise, we were expecting to have higher noise than what we have. So our signals above about 0.7 hertz or so are too small, and the digitizer noise ends up being important. At 300 foot level, we have a CaJAGWR out running, so you shouldn't really trust this curve below 50 millihertz or so. But even above that, you see some excess at very low frequencies. Now, the other thing I should mention is that the 300 foot level is not, really shouldn't be considered surface. We expect that there is actually substantial difference between a surface station that we don't have at the moment and what a 300 foot level would give us. So this is something that hopefully we'll remedy over the summer. Now this is something interesting that Jan did. The curve here is what is called the Peterson low noise model. So what Peterson did was he used a very large array of seismometers, most of them on the surface or close to the surface. And then he minimized for every frequency bin over the entire array and over some stretch of time, and came out with this curve, which he considers very low or lowest noise performance that you could get on the surface. Now, Jan, what he did was essentially repeated the same process, but we have only one instrument. So he minimized only over time, and what he got was a curve that's actually pretty close to this minimal to Peterson noise model. And in some cases, on here, actually maybe even better. Now, we expect to actually do even better than this as we move to lower levels.
Sorry, I don't understand what you're showing.
So don't worry about this one. This one is you have an array of seismometers, and for every frequency bin, you write down or you plot the value that's minimal across the entire network and across some stretch of time. So you cannot do better than that, essentially.
Here at Homestake or somewhere
No, elsewhere. This was done by some guy, Peterson, over a very large network.
You got all the signals you could find. Maybe that here the quietest place was in Tanzania, and then this frequency, the quietest place was in Australia, and this other quietest place was. So
most of them were on the surface or close to the surface, not underground.
Yes.
Not anywhere deep underground. So we might be lucky at Homestake, we don't know, but it appears to be an exceptionally quiet place. These are the time frequency maps, so the horizontal motion at 300 and 2,000 feet. The thing to notice here, well, first of all, as I said, above about 0.7 hertz or so, we don't really have a reliable measurement because of the DAC noise. But you can see a lot of structure here, even at frequencies below 0.7 hertz, which is not really DAC noise. And you don't have anything like that here. So we suspect that this has to do with local disturbances, most likely coming from the fact that our station at 300-foot level is close to the surface, close to the shaft, close to the hoist on the surface as well. It may actually be a hint of why it may be good to go underground because of such cleanliness.
Luke?
Yes.
In both objectives, those two bright red bands that a few hertz look very extremely similar in both spots.
These are the microseismic peaks.
It's the waves on the beach.
Yes. Yes.
Yeah.
That's right.
We saw that in previous slide.
Just go back.
Yeah. Well, back to even one more. The horizontal.
I'll show you the actual coherence plot just a minute. So there's a similar situation with the vertical motion, and this is the coherence. So if you look at the horizontal motion between 300 and 2,000, you see this huge peak. That's the microseismic peak. That's exactly this red pattern. Now, as I said, the relevant frequencies are between something like 50 millihertz and maybe 0.7 hertz or so. The peak is very correlated, much more so in horizontal than in vertical, and that by itself is interesting. It may indicate something about the modal structure of the and the direction of the microseismic waves. But we lose coherence as you move away from the peak. And we don't really know why, and really the only way to answer it is to put more seismometers and to look at what happens. One of the possible reasons is that the 300-foot level station is sitting in the Ellison Formation, whereas the 2,000-foot one is in the Homestake Formation. There is a lot of structure in between. So that sort of thing we would have to study in more detail. Yeah.
What's the spatial separation between the two?
So in terms of the height, it's 1,700 feet. In terms of X and Y, it's probably about 3,000 feet.
But also,
or of that order, maybe 2,500.
One expects the wave, the microseismic wave to be mostly horizontal, and then you may have some vertical just because it's locally shifted up, especially at the top. So There may be some real physics, because visually is a recording that tells you horizontally is very coherent, in vertical it's only scatter that goes up and make vertical, and that one is incoherent.
So there's, Jan will be giving a presentation on Tuesday at the LSC meeting, so those of you who are LSC members can see it. There's actually he's done some very interesting studies with the microseismic noise, and I don't want to steal his thunder, so just go there and see it. But it's quite interesting.
It's basically coming from the waves on the beach in the Pacific.
That's absolutely right. It's coming from the waves,
Correlates.
but not necessarily the beaches.
Well, I mean, at the ocean continent boundary.
No.
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 See the talk.
I'll wait for that. The oceans.
But one thing I wanted to point out here is that this is a vertical coherence, rather. So what we care for gravitational waves is what this looks like as if you have two points at the same depth, or more or less the same depth. So something like that we'll have to answer hopefully this year. All right, so what are our plans? Well, we have to improve the robustness of our system. We've lost a lot of data because of problems with the network and things like that. But our DUSEL colleagues are working hard on these things, and they are learning with us. I mean, in some sense, we are their guinea pigs. But we expect that over this coming year, this kind of problems will go away. They have a new network coming online and so on. Our plan is to build at least 2 more stations at the 4,100 foot level, so deeper than where we are, but also this will be the first time we have 2 stations on the same level. We'll have to add amplifiers to deal with the DAC noise, and probably add some additional environment monitors like microphones and so on. And a big push, I think, this year should be in the direction of developing this finite element model that will tell us what the gravity gradient noise will be for the given level of seismic noise. So
at this level, you're modeling the rock.
Yes,
and all
move the rock.
And things in the rock, and the whole structure of the rock around it.
Yeah, we haven't gotten that far, anywhere near. But what we want is to have essentially a grid of points. Move each one of them, give it some mass, and see what that means for gravitational field somewhere in the middle. And it looks like, based on those few plots I showed earlier, it looks like that we need to go about maybe two wavelengths away from the middle. Then after that, everything becomes stochastic, so it cancels out. And of course, yeah, to be seen, right? And Giancarlo has done some calculations in the past on this, so not finite element models, but just direct solutions to the differential equations, and we'll have to link with him as well. All right, so to conclude, based on these papers from Peter Solson and others, we need to suppress gravity gradient noise by a factor of 1,000 at 1 Hertz. Can you do it on the surface? In principle, it is possible. In practice, it appears to be very difficult, but I think it's warranted to actually pursue this and really study it and try to answer these questions. Underground is definitely better, but how much better? I've given you several arguments. There are no atmospheric fluctuations. The environment is much more controlled. There are no local disturbances that would ruin the correlations and so on. The seismic noise is a bit suppressed, maybe factor of 10, maybe more, maybe less. We expect very long correlation lengths for the seismic waves, so that should simplify the active suppression. It should also allow us to, at least at some frequencies, have the whole interferometer move in phase. And we have to do this finite element model to link all of this with the gravity gradient noise. So do I have the answer for you today? No, I don't. We have to really do this study more carefully. We need to measure the gravity, the seismic noise on the ground and how it changes, how the correlation length changes and so on. But we expect that over the coming year or maybe 2, we should actually have these answers. As I said, please go see Jan's talk for more information. So that's it.